Hi dear students, this is the first part of the sixth module of the subject ME 206 Fluid Machinery. In this module we will be discussing about rotodynamic compressors. Usually the rotodynamic compressors are classified into two categories. One is centrifugal pump compressors and the other one is axial flow compressors. In the first part we will be discussing about the centrifugal compressors. You can see in the figure the basic components of the centrifugal compressors. Actually it is having the main components as impellers. Impeller is nothing but the vanes are the curved vanes are fixed on a drum or rotor. That is what is known as the impeller. You can see a center portion. This is the rotor on which this is the impellers or blades attached is called the impeller. This entire structure is called the impeller, and at the outer periphery of the impeller you are having a separate structure called the diffuser. You can see some fixed blades are there, and the air while passing through these blades, the area of the flow is gradually increasing. That means the kinetic energy is decreased with the expense of, so correspondingly there will be an increase in the pressure energy, and once it passes through the diffuser it will be entering into a outermost layer called the diffuser. There also you can see there is a gradual increase in the cross sectional area. This portion, in this portion and all, the cross sectional area of the diffuser is going, sorry, the cross sectional area of the casing, this is called volute casing, is very less, whereas as it goes on the area of the cross section gradually increases. So while the air passing through the volute casing, there will be further increase in the pressure. So these are the basic components of the centrifugal compressors. That is, the main component is the impeller. The impeller is nothing but the vanes attached on a rotor. That is what is known as the impeller. The rotor will be rotated by an external power source, usually the motor, and the rotor will be rotating at a very high speed compared to the pump. Here usually the speed rate will be around to 20,000 to 30,000 rpm. Okay. In these compressors, the required pressure rise takes place due to the continuous conversion of the angular momentum imparted to the air by the high-speed impeller rotating at a speed of 20,000 to 30,000 rpm. So here the pressure rise is due to the high-speed rotation of the impeller. Due to the rotation of the impeller, what is happening is the impeller will be imparting some momentum to the air already trapped inside the cavities of the impeller or into the vacant spaces or between the spaces of the impeller. So very high rotating impeller will be providing angular momentum to the air trapped in that region. So the air is being getting pressurized. Now the impeller consists of a disc on which radial blades are attached. The air enters the impeller at the center called the impeller eye. The air is initially entering at the center portion of the impeller, that is this portion. So this is what is known as the eye of the impeller. So from backside through a pipe the air will be entering due to the pressure difference. In the inner portion we will have the low pressure. Due to that low pressure, the atmospheric air will be sucked into the eye portion of the impeller, that is what is at the center portion. So this portion is called the eye of the impeller. So air will be entering into the eye of the impeller. As the air flows through the blade passages towards the tip of the impeller, it gains momentum and its static pressure also increases. This is the starting portion, and this one is the tip of the impeller. Outermost portion is the tip of the impeller. So as the air passes through the eye of the impeller to the tip of the impeller, what happens is, since the blade is rotating with a very high speed, some angular momentum is imparted to the air between these blades. So there will be an increase in the static pressure of the air trapped in that region. From the impeller, the air enters a diffuser which provides a gradually increasing cross-sectional area to convert the velocity energy to the pressure energy. See, initially the velocity of the air entering into the eye of the impeller will be a low value, low velocity, but as the air flows through the impeller, from the eye of the impeller to the tip of the impeller, what happens is, due to the high rotation of the speed, momentum is imparted. That means the velocity of the air is also getting increased. Correspondingly, there will be an increase in the static pressure also. But this so as the air leaves from the tip of the impeller, the air will be having a very high speed. With that very high speed, the air will be entering into the diffuser. As I have already told, diffuser is nothing but a gradually increasing cross-sectional area flow passage usually the blades will be fixed one. So as the area increases, the pressure, kinetic energy decreases. Correspondingly, there will be an increase in the pressure energy. That is what is happening in the diffuser. So in the diffuser, the increase in the pressure is with the expense of the kinetic energy, whereas in the impeller, the increase in the pressure is due to the momentum transfer by the blade to the air. So the air then enters after passing through the diffuser. Air then enters to the volute casing, where further conversion of the velocity into static pressure takes place due to the divergent shape of the volute that I have already explained. The volute casing is also having a gradually increasing cross-sectional area. So at the end of through the end of the volute casing, air will be discharged to the outside. Okay. In practice, about half the pressure rise occurs in the impeller vanes and half in the diffuser vanes. So if the P1 is the initial pressure and the pressure is increased to a value of P2 as the final pressure, so half the P2 value will be half the pressure, that is half the pressure P2 will be happening in the impeller vanes, and half the pressure rise will be in the diffuser vanes. In a single stage centrifugal compressors, usually the pressure ratio that we can achieve is 4:1, whereas in the multi-stage up to a 10 bar we can attain. Okay. Now the velocity and pressure variation. The changes of pressure and velocity of air passing through the impeller and diffusers are as shown in the figure. You can see the initial portion is the impeller portion, and the final is this one is the diffuser portion. So as the air enters, first figure is the pressure rise. So as the air enters into the eye of the impeller, this point is the eye of the impeller. From there up to here, it is passing through the vane or the impeller. So this point is correspond to the tip of the impeller. So as the air passes through the impeller vanes, from eye of the impeller to the tip of the impeller, what happens is, due to the momentum transfer, there will be a change in pressure, or pressure rise in the impeller will take place. That pressure rise is shown by this much portion. Now the high velocity air leaving the impeller will be now entering into the diffuser. From there, due to the with the expense of the kinetic energy, further pressurization takes place. So this much is the pressure rise in the diffuser due to the expense of the kinetic energy. So this much pressure rise is actually due to the momentum transfer by the impeller, and this much is the pressure rise due to the expense of the kinetic energy. Okay. Now talking about the velocity of the air passing through the impeller and the diffuser. Initially I have already told that the air entering into the eye of the impeller will have a very low velocity. So C1 is actually the initial velocity with which the air is entering. Now as the air passes through the impeller, due to the momentum transfer by the impeller, the velocity of the air will be increasing. So finally, once the air leaves the tip of the impeller, it will have a very high velocity, that is shown by this point C2. Now as it passes through very high velocity air, now then passes through the diffuser. So I have already told the increase in the pressure in the diffuser is with the expense of the kinetic energy. So kinetic energy will be decreasing, that is velocity will be decreasing to a lower value. Correspondingly, there is an increase in the pressure. So in the diffuser there is a decrease in the velocity, in the impeller there is an increase in the velocity. Usually the air leaving the diffuser will be having almost the same velocity as that of the air entering into the impeller. Okay, that is what is the what is all about pressure change and the velocity change. You can see in the both impeller there will be a pressure rise from P1 to P2, and in the diffuser there is a pressure rise from P2 to P3. But as far as velocity is concerned, increase in velocity is there in the impeller, but in the diffuser the velocity is going to be decreased. Now we will move on to the important topic, that is work input to the centrifugal compressors. So how much work is required for the operation of the compression of the centrifugal compressors. So this equation initially I will derive with the help of the velocity triangle. That's why it is called based on velocity triangle. And this work input calculated, or the final expression that we are going to get, is usually called impeller work input, or simply Euler's work. Okay. This is the one word for this work input to the centrifugal compressors based on the velocity triangle is called impeller work input, or Euler work input. So in a centrifugal compressor, the air enters radially and leaves axially. This is a very important statement. Always it will not satisfy, but usually a centrifugal compressor, the air enters radially. That is a practical case. But sometimes if pre-whirling is there, some difference will be there, of course. But usually the air enters the compressor, centrifugal compressors radially and leaves axially. Moreover, the blades and diffusers are so designed that the air enters and leaves them tangentially for the shockless entry and exit. Now let u1 equal to mean blade velocity, and once we know the speed of the rpm of the centrifugal compressor, then we can calculate u1 equal to pi d1 n by 60, where d1 is the inner diameter of the impeller, or simply the mean diameter of the eye of the impeller we can call. Inner portion is the eye of the impeller. So actually the eye diameter will be the d1. So pi d1 and pi dn by 60, pi d1 n by 60 will give u1. u1 is the mean blade velocity at inlet. Similarly, u2 is the mean blade velocity at outlet, and it is calculated by the equation pi d2 n by 60, where d2 is the tip diameter of the impeller, outer diameter of the impeller we call it as. Now v1 equal to absolute velocity of air at inlet to the rotor or impeller, and v2 is the absolute velocity of air at outlet of the rotor or impeller. These things and all we have discussed in second and third modules. Everything is same. Actually centrifugal compressors are same as that of the centrifugal pump. We have already covered that topic. So the main difference is, in the centrifugal pump we will be dealing with the fluid with higher density, that is water. But here we will be dealing with air, so the density of the air is very less. In the case of the centrifugal compressors, the impeller speed will be very high, as I have already told, 20,000 to 30,000 will be the rpm, whereas in the case of the centrifugal pump, the rotation speed will be very less, much less compared to the centrifugal compressor. That is the major difference. So in the case of the compressors, we cannot neglect the kinetic energy factors. So VR1 relative velocity of air at inlet, VR2 relative velocity of air at outlet. All these things are very much familiar to you. VW1 equal to velocity of whirl at inlet, or tangential component of absolute velocity of air at inlet. VW1 is the tangential component of absolute velocity and VW at inlet, and VW2 is the velocity of whirl at outlet, or tangential component of the absolute velocity of whirl at outlet. VF1 velocity of flow at inlet, VF2 velocity of flow at outlet. Alpha absolute angle at inlet, beta inlet angle to the diffuser, theta angle which the relative velocity VR1 makes with the direction of motion of the blade, or simply it is called vane angle at inlet, and phi the angle which the relative velocity VR2 makes with the direction of motion of the blade, and it is called vane angle or blade angle at outlet. Let m dot equal to mass flow rate in kilogram per second. Actually it is not m dot, mass flow rate. Now this is the velocity triangle for the centrifugal compressors. This velocity triangle we have already seen in the case of the centrifugal pump. It is same as that of the centrifugal pump, only difference is, as I have already told, in the centrifugal compressors usually the air will enter radially at inlet. So there will be the velocity triangle at inlet will be a right triangle with VW1 equal to 0. There won't be any whirl component, since the entry velocity, absolute velocity, is tangential to the entry point line. See, this is the tangential line and this is perpendicular. V1 is perpendicular to that tangent. That means the tangential component of this V1, that is what is known as VW1. So there won't be any tangential component for the V1. That means VW1 equal to 0. So alpha equal to 90 degree. This angle is theta. This is VR1 and this one is U1. I think this inlet velocity triangle is very much familiar to you. Now as the water flows through the blade and at the exit, in this direction water have the tendency so to leave. This is what is known as the relative, this direction will have the relative velocity, but absolute velocity component will be in this direction. So the horizontal component of this V2 or tangential component of this V2 is called VW2. So from here to here we will have the VW2, and vertical component of V1 is the velocity of flow called velocity of flow. This is VF2, and the closing side of the relative velocity and absolute velocity is U2. Okay, so this much will be the U2. So here this is beta and this one is angle phi. This velocity triangle is already we have seen in module 2 and 3. So this is very much familiar for you. And here one more thing you have to remember is here V1 is equal to Vf1 and Vw1 equal to 0, and R1 is the inner radius and R2 is the outer radius. So the R1 the diameter corresponding to this R1 is called D1, and diameter corresponding to the from the center to the tip of the blade, this is tip of the blade, is R2, sorry, D2. That diameter is called D2. Okay, so the minimum diameter given is D1 and the higher diameter is D2. Okay, so I think the velocity triangle is very much clear for you. Now moving on to the derivation part of work required. We know that torque exerted by the impeller on air equal to change in angular momentum. So torque means, since it is rotating, we have to think about the rotary force, that is known as the torque. So torque exerted by the impeller on the air is equal to change in angular momentum. So change in angular momentum is equal to torque exerted. So angular momentum is nothing but angular momentum is the product of radius and tangential momentum. So momentum is mass into velocity. So tangential momentum means tangential component of velocity into mass. So actually in both inlet point as well as the outlet point, the tangential component of the velocity is nothing but Vw. The tangential component of absolute velocity is Vw. At the inlet side, the tangential component is Vw1. At the outlet side, the tangential component is Vw2. Okay. Now, so tangential momentum is component of velocity is Vw. So tangential momentum is mass into tangential component m into Vw. Now m into Vw, tangential momentum multiplied by radius of rotation will give angular momentum. So angular momentum is equal to r into m into Vw, or simply it is m r Vw. Okay, now if you are assuming that constant mass flow rate m1 equal to m2 equal to m, so m is constant, can be taken outside. So torque T is equal to m into difference in angular momentum. Actually change in angular momentum we require. The final angular momentum means at the outlet side, angular momentum at the outlet side, that is Vw to R2, and at the inlet side the angular momentum is Vw1 R1, where Vw2 is the outlet world component of velocity at outlet, and Vw1 is the world velocity component at inlet. R1 is the inlet radius, R2 is the outer radius. Okay, now work done, this is torque. Now we know that work done is actually equal to force into displacement. Actually in the rotary motion, force is torque, and the displacement is angular displacement theta. So work done per second means torque into theta divided by time, but theta by time is angular displacement by time, that means angular velocity. So work done per second equal to torque into angular velocity of the rotor. Now work done per second equal to, we know that torque equal to m into Vw2 R2 minus Vw1 R1 into omega is the angular velocity of rotation of the rotor. But we know that u is equal to r omega. So on substituting, on multiplying omega to the inside the bracket, we will get m into Vw2 R2 into omega minus Vw1 R1 into omega. But u is equal to r omega means R2 into omega is u2 and R1 into omega is u1. So the final equation becomes work done per second equal to m into Vw2 u2 minus Vw1 u1. So this is the general equation. Now you will have a confusion that I have already told that the velocity of the air will be entering at the eye of the impeller in the radial direction, so Vw1 is equal to 0. I have already told, there is no need of confusion. I have already told that this is the general case, but sometimes the changes also will be there if pre-whirl and all is there. In that case we will have Vw1 component towards the right side of this one. That case we will be discussing in the numerical problems and all. So here if assume that if Vw1 is there, or sometimes possibility of Vw1 is also there, in that case this equation gives you the general equation to calculate the work done per second. Work done per second equal to m into Vw2 minus Vw1 u1. This is the general equation, or this equation is known as the Euler's equation. And here since the air enters radially to the eye of the impeller, Vw1 equal to 0. So in that case, if in the problem it is given that air enters the impeller radially, then in that case you can directly take Vw1 equal to 0. So in that case the work done per second equation reduces to m into Vw2 u2. This is a sub case of this one. This is the general equation, and if the air enters the impeller radially, then the equation for the work done per second reduces to m into Vw2 u2. Okay. Now these two equations you by hearted. These are the two important equations. Now from the velocity outlet velocity triangle we have Vr2 square equal to Vf2 square minus U2 minus Vw whole square. I will show you here. Vr2, this is a right triangle. This Vr2 is the hypotenuse, Vf2 is the one edge, and the other edge is this one. This is actually u2 minus Vw2. This small distance, entire distance is u2, and from here to here it is Vw2. So this small distance will be u2 minus Vw2. So from this triangle you will get Vr2 square equal to Vf2 square plus u2 minus Vw2 whole square. That is what is written here. Okay, Vr2 square equal to Vf2 square plus u2 minus Vw2 whole square. But Vf2 square equal to V2 square minus Vw2 square. See, from this triangle Vf2 square equal to V2 square minus Vw2 square. So I will be substituting here, instead of Vf2 square I will substitute V2 square minus Vw2 square. Therefore Vr2 square equal to instead of Vf2 square I am substituting V2 square minus Vw2 square plus I am expanding this entire term, that is u2 square plus Vw2 square minus 2 into Vw2 u2. So in this term you are having Vw2 one Vw2 u2 term. So this can be taken to the left side, and Vr2 square can be taken to the right side. So what happens? Vw2 u2 equal to V2 square minus Vr2 square plus u2 square by 2. You simplify it in a paper, then you will get this equation. Vw2 u2 equal to V2 square minus Vr2 square plus U2 square all divided by 2. If, similarly, if one Vw1 component is there in the inlet side, then you can say that Vw1 U1 equal to V1 square minus Vr1 square plus U1 square by 2. That will be the expression at the inlet side, that is Vw1 U1, if Vw1 is there. If radial inlet, there is no need to consider that term. Anyway, I am talking about the general cases. Similarly, if entry of air is not radial at inlet, then Vr1 square equal to V1 square plus U1 square minus 2 Vw1 U1. From that you will get Vw1 equal to V1 square minus Vr1 square plus U1 square by 2. Okay. Now work done per kilogram equal to, see here I am talking about work done per kilogram, not work done per kilogram per second. Okay. So actually work done per second was m into Vw2 minus Vw1 U1. Here work done per second per kilogram means we will be dividing that work done per second divided by the mass flow rate m dot. So m and m will get cancelled. So work done per second per unit mass or per kilogram equal to Vw2 minus Vw1 U1. So that will be equal to, see here Vw2 is V2 square minus Vr2 square plus U2 square by 2, and Vw1 U1 is this one. So substituting you will and rearranging, you will get Vw2 minus Vw1 U1 equal to V2 square minus V1 square by 2 plus Vr1 square minus Vr2 square by 2 plus U2 minus U1 whole square by 2. You can see this is just a reverse actually. Here V2 minus V1, here it is Vr1 minus Vr2. That means actually the relative velocity Vr1 at the inlet will be more compared to the relative velocity at the outlet. Okay, Vr2. Now first term of the above equation represents increase in kinetic energy of the fluid in the impeller. So this is nothing but the increase in kinetic energy of the fluid within the impeller. So this is actually the momentum imparted, and correspondingly equal to this much quantity there will be a static pressure rise in the air while passing through the impeller. Second term represents the pressure rise in the impeller due to diffuser action. This term represents the pressure rise in the impeller due to the diffuser action, and third term represents the increase in pressure due to centrifugal action. This one is the increase in pressure rise due to the centrifugal action. Okay, anyway, this equation is not at all used in for doing the problems and all, but this equation is very important. Work done per second or work done per second per unit mass or work done per second per kilogram equal to Vw2 minus Vw1 U1. This equation is an important one. This is not much practically used, but still if it is asked you have to derive it, that's all. Okay, now the last one was an expression for the work input Expression for the work input from the velocity triangle. Now we will consider this, that was called the impeller work input or Euler work input. Now we will see the work input based on the steady flow energy equation. This work input is called actual work input required. Okay, this work input is called actual work input required. Now from the steady flow energy equation applied between the inlet and exit of the compressor, we have H1 plus V1 square. 1 is the inlet and 2 is the exit. Now H1 plus V1 square by 2 plus H1G plus W equal to H2 plus V2 square by 2 plus H2G plus Q. This equation you are studying in thermodynamics, steady flow energy equation for an open system. Now where W is the work component and Q is the heat component. So here no external heat is added, so this term vanishes, and Z1 equal to Z2. If inlet and exit are on the same, almost on the same level, that means Z1 equal to Z2. So these two term vanishes. So then the equation reduces to H1 plus V1 square by 2 plus W equal to H2 plus V2 square by 2. Hence work done W equal to H2 plus V2 square by 2 minus H1 plus V1 square by 2. Actually H is equal to CPT. So H2 equal to CPT2 and H1 equal to CPT1. I am taking that CP outside from both terms. So from first term H2 equal to CPT2, I have taken CP outside. So inside the bracket T2 will be there, plus with the second term there is no CP. So I will be dividing with CP in the dividing with CP to the second term. That means T2 plus V2 square by 2 CP minus, similarly I am taking CP from this term, that is H1 equal to CPT1. From there I am taking CP outside, so T1 will be there. Here there is no CP, so this term becomes V1 square by 2 CP. Now this T2 plus V2 square by 2 CP and T1 plus V1 square by 2 CP has a very important meaning. This is what is called the stagnation temperature. Okay, T plus V square by 2 CP is simply known as the stagnation temperature. So for studying this equation you must have a basic idea what is stagnation condition. So stagnation condition is nothing but if a flowing fluid is allowed to bring to rest isentropically. If a fluid is taken to rest or zero velocity isentropically, then that process is known as the stagnation process. Final condition is stagnation condition, and the process is known as the stagnation process. So stagnation, every property corresponding to that stagnation state is known as stagnation properties. So T, usually it is represented by a suffix 0. That means P0 is the stagnation process, T0 stagnation temperature, like that. So T plus V square by Cp is actually stagnation temperature. So T2 plus V square by 2 Cp is T02. T1 plus V1 square by 2 Cp is T01. So this equation can be equation reduces to work done W equal to Cp into T02 minus T01. If you are very much interested about this stagnation condition, you just refer some text. Actually stagnation condition is a flowing fluid usually will have enthalpy plus kinetic energy. So H plus kinetic energy means half mv square. For unit mass it is v square by 2. So H plus v square by 2 will be the total energy of the flowing fluid if heat and all is not considered. So that in that term, if a flowing fluid is isentropically decelerated to zero velocity, then the final state is known as the stagnation condition. So once the fluid reaches to the stagnation condition, velocity will be 0. That means H increases. Correspondingly, there will be an increase in the enthalpy. That velocity loss in velocity is actually added along with the enthalpy. So stagnation enthalpy can be defined in another way as the maximum enthalpy of the fluid, or usually it is taken as a reference condition. So that is what is known as H naught. So H naught is equal to H plus V square by 2. We know that H is CPT. So CPT0 equal to CPT plus V square by 2. To the right side I am taking, to the left side it is CPT0. So from that I am taking Cp to the right side. So T0 equal to the right side first term is CPT, H1 is Cp, H is CPT. So Cp into T divided by Cp, Cp and Cp cancel. So T0 equal to T plus V, second term is V square by 2. So V square by 2 Cp. Dividing by Cp, it becomes V square by 2 Cp. So T0 equal to 2 plus V square by 2 Cp. That is the general condition. So since every term, here it is T2 and here it is V2. So this entire term is T02, this one is T01, T1 and here it is V1. That's why it becomes T01. So equation becomes work done is equal to W into Cp T02 minus T01. This equation is an important equation. So in some problems, we have to calculate the work required based on this equation. So in that case, if the stagnation conditions are directly given, then you can use this equation. The same can be calculated using the static conditions also. So which equation to be used depends on the condition given along with the problem. Okay, if static conditions are given, then we can use the static equation to calculate the work required. Otherwise, if the stagnation conditions are given, then we have to go for the stagnation equation. So W equal to work required per second is equal to Cp into T0 minus T02 minus T01, where T02 and T01 are the stagnation temperatures. I am taking this T01 outside, so it becomes W equal to Cp T01 into T02 by T01 minus 1. Now this is equal, this can be rewritten as W equal to Cp T01 into, actually for a isentropic process, the relation between T temperature and pressure is T2 by T1. T2 is the final condition and 1 is the initial condition. Then T2 by T1 equal to P2 by P1 all raised to gamma minus 1 by gamma, where gamma is the isentropic index. If it is not given, we will take it as 1.4. So similarly, for T02 by T01, I can write it as P02 by P01. See, for T02, I am writing P02. For T01, instead of T01, I am writing P01. That's all. P02 by P01 all raised to gamma minus 1 by gamma minus 1. So this equation is also an important equation. Sometimes we can calculate the stagnation pressure, and if stagnation temperature at inlet is given, then we can directly calculate the work required by using this equation. So these two, first this equation and this equation, both equations are very important equations. Please by heart it. And the same equation can be expressed in terms of static properties also. So based on static properties, work input is given by W equal to Cp into T2 minus T1. See, here it was Cp into T02 minus T01. So both temperature is on stagnation. Stagnation temperature at 2 minus stagnation temperature at 1. Here instead of stagnation, I am directly writing static temperature. W equal to Cp into T2 minus T1. And here it was W equal to Cp into T01. So here it becomes W equal to Cp instead of T01, I am writing T1. And instead of P01, it becomes P2. And instead of P01, it is P1. So P2 by P1 always to gamma minus 1 by gamma minus 1. So this equation, for this is equation 1, this is equation 2, this is third one, and this is fourth one. These four equations are very important equations. And if in the problem, a numerical problem, stagnation conditions are given, then you can go for the first two equations. If in the problem static conditions are directly given, then you can use the third and fourth equation. So it depends on the properties given in the problem. Okay.